Hey, ladies and gentlemen, I'm here today to talk to you about section 10.3 in your genetics textbook. This section title is Processing a Protein. So we've talked about transcription, we've talked about translation, and now we're talking about how that protein folds and changes shape after it's been released from the ribosome. All right. So a reminder of protein structure. There's this word, the word is conformation, and the word conformation is used to describe how a protein folds on itself and gains a three-dimensional shape after the ribosome is done completing the amino acid sequence. So once again, after those amino acids are sequenced in the correct order, that amino acid chain is going to leave the ribosome and enter a new phase of conformation or folding into a specific shape. That shape is going to be determined by, hello, cat, the attraction and repulsion between the atoms of the proteins. So as you may remember from chemistry, or if you took physical science, atoms have a bit of a charge depending on where atoms are oriented in the molecule. And so this has to do with ionization. If you want to learn more about it, just type in ionization into Google. But essentially, atoms have a slight negative or positive charge. And because of that, when you have atoms all lined up in a straight line, eventually some of those charges are going to find themselves attracted or repulsed to each other. And that's going to help determine the shape. There's also chemicals that come into play here and proteins that come into play with shaping. So we'll talk about some of those as well. There's 4 levels of protein structure on the way from the ribosome, where the amino acid chain is a straight line, all the way to the final product. The primary structure, the secondary structure, the tertiary structure, and the quaternary structure are what we're going to look at today. So this is a picture that you've seen if you've read textbook chapter 10.3. What this is showing is the progression of the protein folding from start to finish. So up here, you've got the primary structure. This is what the amino acid chain looks like coming off of the ribosome. The secondary structure here is that initial coiling or shaping right after that chain leaves the ribosome. And so the secondary structure could either be loops and coils like this, so a spiral, or there's something called a beta pleated sheet. And every time you guys see these lines, these dotted lines, by the way, those represent weak hydrogen bonds. And those weak hydrogen bonds, again, they don't make it into a new molecule. It just kind of makes the molecule reshape in structure so that that protein starts to have a fold. Let's go back to tertiary structure. This is when you go from the spiral or the pleat into something that is more three-dimensional, and there's continued bonding between other atoms in that molecule as they find each other either attracted or repulsed. And then D is a quaternary structure, and this is where the protein complex might form bonds with other protein complexes. So perhaps you have 2 amino acid chains leave the ribosome, and those 2 amino acid chains, which are the same, might come together and form a larger protein based on multiple chains coming together. Looks like this slide is not showing up all the way. I'm going to pull this image over just a little. There we go. Okay, so protein folding. Once again, proteins begin to fold right after they leave the ribosome. The first few amino acids in the protein essentially are what are called a signal sequence. And that signal sequence is basically then embedded into a membrane. And so once it's embedded into the membrane, then that protein is somewhat kind of held in place while the rest of the shaping can occur. During folding, so during these processes, both secondary and tertiary, there are sometimes the presence of these what are called chaperone proteins. And chaperone proteins, in addition to the attraction and repulsion impulses of those atoms, chaperone proteins are available to help produce that shape. And so if you look at this image here, you can kind of see the orange is the chaperone protein right here. Chaperone proteins allow almost like a template for the protein to wrap around, so that if you kind of look here at the several chaperone proteins, it's dictating which way, which curvature that protein is orienting in on its way up to the final folded product. Chaperone proteins stabilize regions so that those regions can stay in form as other regions begin to shape as well. The chaperone proteins also prevent the protein from getting stuck if they were to sort of bend or fold in a way that those attractive or repulsive pulses are too strong and they can't unwind. Those chaperone proteins help keep those folds in place so that they don't fold over too hard or fold over and reach some other kind of attraction or repulsion that's not intended. Chaperone proteins are used a lot in genetic medicine, so you might learn a little bit more about that in our activity. Chaperone proteins can be used to help treat diseases that result from misfolded proteins. So if we have a disease that is due to proteins that have been misfolding, chaperones can be introduced as a drug to try to help with that protein fold so that there's no longer that issue of misfolded proteins. Because as you can imagine, if a protein doesn't have the correct shape, it doesn't have the correct fold, that protein can become useless and harmful to the body. So chaperone proteins are being researched in medicine. Hopefully we get to learn a little bit about that more in the activity at the end of the chapter. Within protein folding, of course, there are bound to be mistakes. And so there are things in place in the cell to help with these mistakes. So proteins that become misfolded or the wrong shape are tagged with something called ubiquitin. And ubiquitin is basically a label that says, yo, cell, this protein is not folded correctly. We got to do something about it. And so what ubiquitin does, it serves as a marker. And then if a protein gets several ubiquitin tags, it's going to be taken to a structure called a proteasome. And a proteasome is essentially like the waste or recycling center for misfolded proteins. Think of it like a tunnel that the protein can enter in. And remember that protein that before it was folded was a long chain. And so that's proteasome sort of pulls that protein back into its original chain of amino acids and basically ends up pulling those proteins apart, breaking those bonds and re-releasing the amino acids back to the cell to be reused. So it's basically like the recycling center for proteins that are misfolded. We don't want misfolded proteins in our cells. It is harmful. It is not good. So proteins can misfold by a couple of different ways. The one way that a protein can misfold is if there is a mutation. And so if there's a mutation in the genetic code, even if it's one letter at all, that mutation can cause there to be an imbalance in those attractive forces between molecules. And if there's even one wrong fold there, that'll cause a big problem. Or if there is more than one conformation, meaning if that's a complex fold, then it's likely that there could be misfolding as well. Now, what we're going to look at in one of our Edpuzzles is all about prions, and prion protein can fold into any of several conformations. And what we're going to learn about prions is they're very much susceptible to mutations. And we're going to learn about how they can cause diseases that are very harmful and deadly to the body. Once a protein has been misfolded, and if it happens to be a prion protein, these prion proteins can actually change properly folded proteins into misfolds. So what that means is if we have a protein in the body that has been misfolded and it's a prion protein, this can go to other proteins and essentially convert them into infectious proteins. That's what propagation means. Propagation means that those proteins that are made that are misfolded can now go and essentially infect properly folded proteins and convert them into their misshapen, basically to be misshapen. Here's an example of what prion proteins can do. So this is Scrapie here. It's from in sheep's. So this is an example of a protein that has been misshapen. Now, if you notice here, this misshapen or misformed protein is now bonding to a normal PRP. That's a prion protein. So if this Scrapie mutated protein bonds to a normal prion protein, actually can convert that prion protein into the Scrapie PRP, which is not good. Scrapie PRP is what causes disease. So now we have two mutated proteins, and look, now those two mutated proteins can go and infect other proteins. So eventually those proteins which were healthy have now been misformed by the Scrapie PRPs. Those original one malformation can now go and infect other cells and other proteins. And this is a big problem. And it's got a lot of ramifications genetically. In your Edpuzzle, you're going to see that these are deadly diseases and ones that scientists are researching a lot about right now. So in several disorders that affect specifically the brain, those misfolded proteins, those misfolded prion proteins, the PRPs, can start to pile up and stick together, and it's called coagulate. And if these protein masses get too big, what can happen is they can clog the proteasomes. Now, remember, proteasomes are those recycling centers for misformed proteins. But if those masses, those prion proteins, start to stick together and become too big, they can't get into those proteasome recycling centers, which will inhibit the function of the proteasomes, which will now disallow other malformed proteins to get in there. So that's a big problem. If we are to look at different disorders, specifically involving the brain and misfolded proteins, you're going to see that there's different proteins affect different things. So if you have a misfolded protein, the specific protein is going to have a specific effect and be a specific disorder. Here's some examples of specific proteins and what happens if they become misfolded. So Alzheimer's disease, a disease that affects a lot of us. It affected my family 2 years ago, lost my grandma to Alzheimer's. That we have found out can be the result of the amyloid beta precursor protein. So if the amyloid beta precursor protein, which you can see it right here, is misfolded, what we can see is patients end up with Alzheimer's disease. Not always, but a lot of the time. There's other proteins here, one from your book. The Lewy body dementia is the alpha-synuclein. And if that alpha-synuclein is misfolded, that's the disease that will take place. Huntington disease is caused by a misfolded protein, aptly named huntingtin. So just some things to keep in mind that if it is, depending on the protein, that will be the disease that is seen as a result. Now that's where I'm stopping for today. Now it would be great if at this point you are feeling good about chapter 10.3, but you may need to do some rereading if you aren't feeling good about this section. My recommendation to you, reread, maybe even rewatch, and then complete the Edpuzzle that has to do with prions and genetic disease. That's it for me. Have a great day.